Okay, we're going to go on to example 4 now. Very similar application of the first derivative test, trying to find critical points, except in this case we're going to use a different function, and we'll see some new things. So we're going to try to find again the extreme values of the function f of x, but in this case it is the function 1 over the square root of 4 minus x squared. So the first thing that we can do is try to figure out where the function in this case is defined, because remember that the domain of our function is going to be important when we're finding the domain of the derivative. So in this case, we can't have the square root of a negative number. So we need only values in the radical that would be greater than or equal to 0. But now because it is divided by, we have 1 over that, we can't include 0 either because that would cause division by 0. So our domain is subject to that condition. And if we solve for x, we're going to get that x squared we'll have this equals 4. So x squared has to be less than or equal to 4, which will give us that x has to be less than 2 but greater than negative 2, and that's going to be non-inclusive because again we can't have anything be equal to 0. So our domain is non-inclusive 2 to 2. Okay, so we can go ahead now that we know the domain of the function f, we can go ahead and take the derivative Okay, so I'm going to rewrite this as the quantity 4 minus x squared to the negative 1/2, and then I'm going to use the power rule and the chain rule to take the derivative. So I'm going to get a negative 1/2 coming out in the front, and the power is going to reduce to 3/2, and then I need to take the derivative of the inside, and that's going to give me negative 2x. And when I simplify that, I'm going to get x over 4 minus x squared to the 3/2. So in this case, we can see that we have a critical point. Now, you might say, let's worry about division by 0, but that's already taken care of our domain. The domain of this function isn't any more restrictive than the domain of the original function, so we're going to keep the original function's domain. And so the only critical point here is when x is equal to 0. X equals 0 would cause the function f prime to be equal to 0. We'd end up getting 0 over 4. And that's 0. So that's our critical point. In this case, we do not check our endpoints. Because they're non-inclusive. And like we saw in example 1 and 2, we're not going to have any extreme functions at the non-inclusive endpoints. So our only candidate for a critical point is at x equals 0. And the value of the function at x equals 0 is 0. In order for us to determine whether or not this is a max or a min, we need to know what the function is going to do as we move away from 0. If we look at the numerator, so here's our derivative again. If we look at the numerator is going to become larger, either more positive or more negative off to either side. And the denominator is always going to be some number smaller than 4 or 2, so that value squared is always going to be some number smaller than 4. So when we look at either side, we're going to end up getting only a positive number. So that means when in the numerator, the bottom is always positive. And so in the numerator, if we move off to the left, the slope is negative. And so we know that we've got a function that's going to have a negative slope off to the left. It's a negative slope like that. And if we move off to the right, then x will be positive, and so the slope will be positive. And so that suggests that our critical point is an absolute minimum. We can confirm this by graphing. We could see that our function actually looks something like that. And this is our minimum. Depending on your viewing window, it might be hard to spot that that's actually a minimum because the curve looks pretty flattened out, but it is a minimum. You could have also verified that it was a minimum by looking at the value of the function for a number slightly bigger than 0 and slightly smaller than 0. And you could have evaluated that with your calculator and you would have gotten the same thing, that actually a point slightly off to the left or slightly off to the right is going to have a higher value, so it's a minimum. If you read Theorem 1 in detail, you'll remember that Theorem 1 told us that if we have a function on a closed interval that's continuous, we're guaranteed at least one minimum and at least one maximum. And so you might ask, well, in this case we only got a minimum. Why didn't we get a maximum? And the case is that Theorem 1 says that it has to be a closed interval, and in this case we have an open interval, so we're not guaranteed any critical points at all on an open interval like this.